So the title of my talk is Students Can't Have All the Fun, Educators Experimenting in the Lab. So you'll see why this is relevant as I go through the talk. Basically, as Dino said, I'm not currently in Perth. I'm actually 2 or almost 3 hours away, pretty much in the middle of nowhere, down south near Margaret River in a little town called Balingup. And this is basically where my husband's parents own a little hobby farm here. Now, we've come here to have a bit of a break, but another reason is also to do a bit of few experiments. So my husband is an organic chemist. He's also a natural product chemist as well. His father is also an organic chemist. So this led us to have a very good opportunity to have a bit of fun and try a bit of plant extraction. So my toddler, who's 3, wanted to join in. So there he is trying to join in. He's trying to push all the plants in. And then my little baby newborn is strapped in and also very, very curious about what we're all doing. Now, the feeling that you get when you're learning something new, when you're experiencing or doing a new experiment, is often something of curiosity, amazement, and that kind of thing. And that's something that we would like our students to also feel. So this is where a lot of the work that I've done comes in. So the 2 things I'm going to be presenting today is a project called Advancing Science and Engineering Through Laboratory Learning, or ASL for short. And it's something that I've been involved in for quite a long time. And the second part of my talk is looking at electronic laboratory notebooks, a new project I started a few years ago, but something that I find really relevant and important for today's society. So before I even get onto that, there was a paper published in Science by Rowland. As we all know, Science is a premier journal, and it's one of the rare papers on education that's been published in Science. So I want you to have a quick look at these quotes and think about what's relevant to what we see as education today, particularly about lab work. So key things I want to draw your attention to. There's things about active learning. So being able to solve, do things. Problem solving, solving problems. Convincing the world, which is leading to communication skills. As well as memory alone is not trained. So not rote learning and being able to actually transfer and think about what we've learned into new contexts and things like that. The key thing that Rowland says that really relates to me is that to produce students of action, they must be trained in action, which means they have to go into the lab. And I think that's something that most of us really relate to, which is why we're so passionate about lab learning. So my question to you is, what year do you think this was written? Okay. So have a think about it. If you want, type it in the chat. I want to see what, I can't actually see the chat, but type it in the chat to see what people think. What year was this written?
We have a few 1920s, 1890, 1960, 1920, 1950s, 1900s.
Ah, very good. All right. So this was actually written in 1886. So a long, long time ago. And there's some who were quite close. So even though it was written in 1886, it's all the things that are in this paper are still relevant today. Now, why do you think that's the case? Like, why is it all still relevant? There's lots of questions that we can ask about that. Like, wouldn't these problems already be solved because it was written so long ago? Well, from my point of view, the world is constantly changing. So there's changes that are happening all the time. There's changes in resources, changes in technology, changes in management, so many changes which will contribute to how we do things and what we find. So many changes is most likely the reason why we still haven't got there yet, and something that we're still working towards. So one way of addressing this is through a project I've been working on for a while. So the project started in 1999. So as my husband says, the turn of the century, which sounds so long ago, with the focus on physical chemistry. Then it moved into all of chemistry with a slight name change to all of science in 2009. Then we expanded into schools before we got some funding to actually expand it to the whole of Australia. And now we're not currently funded, but there's a paid model in place to help academics and teachers. Now, I've been really fortunate to be part of this project for a while. So I started out as a student being involved in this project before before managing the whole project and becoming one of the directors after I finished my PhD, which has been amazing. So ASL, or Advancing Science and Engineering Through Laboratory Learning, has two strands. So it started off at universities before moving into schools. So the list on the left are all the university directors, and a new group, an expanded group, were also brought on board when we got funding to expand the project to schools. So the objectives of ASL, there are four main ones, right? The first is to make available a database of scientifically and educationally sound experiments. And this means they have been tested by both academic students as teachers, so that there's a resource that anyone can go to and use. One of the key things I think about the project or program is the professional development that's being provided. So often academics don't have a science education background, so they are lacking in the theory and the understanding of issues surrounding student learning. So being able to provide that professional development and understanding can be very, very useful. Another objective is to provide or build a community of practice so that we can all share ideas, pretty much what Dino and Nicole and various other people have been doing through creating events like this. And of course, we want to look at the research behind it to try and use what we've done to then share and help improve student learning, particularly in the laboratory. Now, the school sector or the school program is basically the same. We have the same objectives, but in addition to that, we also need to make sure that everything is mapped to the curriculum, because it's quite important for the school sector. And it's also something that we want to do is provide teachers with a voice. So often teachers are going by doing what they do best, but also lacking that voice that they may have and would like to share their ideas and things like that. Another objective with the schools is to also provide an interface between schools and university, so that there's that dialogue and connection, which is often lacking in different communities. So the next bit, I'm just going to focus on the first two objectives. So the first one is to build a database of educationally sound and scientifically sound experiments. And the way that we define this is to make sure that the science is accurate, the experiment has to work reliably, it has to be safe, and it has to be able to transfer to a new location. Because if it's on a database, you want to be able to take what's there and also use it in your situation or your context. With the professional development, as I said, the program aims to provide that professional development to academics in improving understanding of educational issues. And that's facilitated through various means. So, for example, we run workshops, we've produced or created an educational template, and we've also developed multiple instruments and surveys to be able to assess and evaluate learning experiences in the lab. So with the workshops, this is where a lot of the learning by academics and teachers happen in how to improve experiments in the lab. So these workshops were initially set up as a third part, as a way for testing experiments by a third party. So not someone from your home institution, but someone from external, so that they can actually give you honest feedback on what they think your experiment is doing, whether it meets the learning outcomes you intend it to meet, and whether students actually think so as well. This is because the experiments are actually tested by staff and students, and they're tested under as realistic conditions as possible within the labs at the workshops. Most importantly, extensive feedback is given to submitters, so those who have actually put forward their experiment for testing. And this is where all the professional development comes in as well. So one thing to also bear in mind is that when we're working at school level and tertiary level, there are differences that we had to keep take into consideration. So tertiary teachers often have a very strong science training. That's what they're trained to do. But they have a weak education background. So they haven't actually had formal education training. Whereas school teachers can and often have a weak science background, but they have a strong education training. So it's really important to keep these in mind. And we've actually tried to incorporate that within the activities that we've done for the program. So a typical workshop program looks something like this for a university. So often it goes over multiple days. The key sessions are the discussion sessions. So this is where all the discussions happening, where all the educational theories being provided and put into context, and so on. So there's lots and lots of discussions happening throughout the whole workshop. There's also the lab sessions where all the experiments are being tested by everyone. So often you most likely haven't done the experiment before, and it can be quite daunting for lots of people. And of course, there's lots and lots of food. So lunch and workshop dinners, and at the feedback session, there's snacks and things like that provided to make sure everyone is happy and willing to share feedback and so on. In the schools sector, it's the same. So we still have the experiments being run. There's still discussion sessions for the educational aspects, and there's also food. The only difference is with the school one, we provide an exemplar experiment for the teachers, and we run that so that they can see what an exemplar experiment may look like that they might want to aspire to. But with both university and schools, all experiments that are run have been submitted by the teachers or the academics so that they get the feedback. Now, how the experiments are run during the workshop is that participants work in groups. So we have students and academics working in groups. So you can either have a student with a student or student with an academic working together. Okay. With the schools version, we have all mixed together. So we have teachers and students working groups of 3 or 4. Now, this is really, really important so that there's a mix, you get different viewpoints, and there's lots of sharing going on. And it's really interesting to hear what actually academics and students think about working with other students or other academics. I think from observation, I think the academics were more scared of doing this and working with students than the student was working with an academic. They were a bit more nervous. So one of the things that really came out of the workshops when we asked people what they thought about it was the academics, this is just one example, the academics really being reminded of what it was like to be a student. So here they are in a workshop situation, completing an experiment that they've never done before, just like a student when they're at university during their studies. And a lot of the academics really felt nervous. They forgot what it was like doing something new, because most of the time you're in a situation where you're the expert and you don't feel that nervousness and the struggle that you may feel when you're doing an experiment for the first time. And in some cases, they said the student was actually teaching them. And it's something refreshing, I guess, that they said was really good to see. The workshops also offer useful means for improving students' learning experiences. So they were given the tools and the tips on how to actually improve labs, the experiments, when they got back to their home institution. Now, I mentioned an educational template. So this is something that's provided as a scaffold for people who submitted experiments to think about when they're designing or revising an experiment. So the template gets people to think about the educational issues. So what are the learning outcomes? How does academic know that the student have achieved those outcomes? How do the students know that they've actually achieved the learning outcomes? Those kinds of things. So at first, those who are new to this kind of situation found it really, really hard to actually put it down on paper and actually think about these issues. So the workshop was there to actually help them and support them in thinking about the educational issues surrounding particular experiments and so on. And I guess the workshops also increase, as I said, that was a key driver. And it was good to see that participants also saw that it did help increase their understanding of educational issues. So that was a university workshop. Now, when we expanded into schools, we also had to think about how can we help teachers, because they also struggle and need help with improving their experiments in the school sector. And one thing that we thought about at the time was this idea of inquiry. So at the time, the new Australian curriculum had come in. So this was where there was more of a, I guess, overview of each state having covering the same content and so on. And one thing that was put in place was the idea of science inquiry. So there was a strand that all teachers had to embed within their lessons, which was science inquiry. And when asking teachers what they thought of it and how they're going to do it, a lot of them really struggled and were, I guess, apprehensive, because science inquiry is one of those things where it's quite difficult to implement, because there's so many different definitions and so many ways of doing it that it's really hard to find one particular way of embedding science inquiry into a given task or a given activity. So what we did was we looked through the literature and we came across a framework that we thought was really, really useful in terms of having an actual way of using it in the classroom. And that was the 6 essential features of inquiry. So this was developed by the National Science Foundation a while ago. And basically what this framework says is that if an activity contains any of these features, it is an inquiry activity. So what are they? So the first is the learner engages in scientifically orientated questions. So questioning is really important. The learner gives priority to data and evidence. So as scientists, we know data and evidence is really, really important. The learner analyzes data, formulates explanations based on the analysis, able to connect explanations to scientific knowledge, as well as communication or communicating and justifying explanation. So that communication and justification. So all of these things are actually what we just saw in the science paper that I got you to have a look at. So these are all really key things in inquiry-based activities. So when we look at this framework, we've broken it down into something that teachers can actually use in the classroom. So teachers meaning teachers at school as well as teachers at university. So if we have a look at it, we've got the questions down, the features down the columns, and there's different levels across the top. So what we do is we can look at the different levels and different features. And for example, if we just focus on questioning, there's different levels. So you could have no question, a teacher can provide the question, a learner can sharpen the question, a learner can select a question, or a learner can pose a question. All right. So we're actually moving from something very teacher directed to something very student directed. And that can shift and change depending on the purpose or what we want the activity to do. So this means we can do that for every single feature. So it goes from very student directed to very teacher directed. And there are different experiments that you want to be very teacher directed, but also there are some experiments where you want students to have a bit more creativity and actually explore and have that inquiry or more open inquiry in there, depending on the purpose. Another thing to also think about is also the level that you're teaching or using the activity. So you can have something very open with a higher level or higher ability class versus something that's a bit more teacher directed for a lower level or lower ability class. So it always depends on your purpose. So what we did was develop a tool which we call the inquiry slider. So it's not that creative. And this was developed a while ago when we had a visiting academic, so Mary Kay Ogle, came to visit us. And we came up with this instrument that helps teachers actually look at inquiry and provide information that that can help them improve their experiments. So the idea behind it is we have our slider, and before doing anything, the educator will be putting themselves into the shoes of the student and think about what is actually happening in the experiment. So in terms of questioning for this typical hypothetical experiment, the learner posed the question. The teacher discusses possible plans. The learner is guided through conducting and recording of data. The learner is guided in the analysis. The learner is guided in reasoning, and the teacher writes the conclusion. So before doing any changes to an experiment, this is the baseline where we've thought about what level of inquiry is actually there. Now from there, you can then tweak your experiment. So you can have a look at the experiment and you can actually see that different experiments have different levels of inquiry. So I've got 2 school-based experiments here that we've run at multiple workshops. So we've got baggy science and a friction or physics experiment. And from just looking at it, you can really see which one is more, I guess, more open or more student directed compared to more teacher directed. So as you can see, like baggy science is a lot more student directed or more towards the guided and open inquiry by just looking at it compared to the friction experiment. And by knowing that, you can then tweak. So it's really quite a scientific process. You have to think about what the level of the current level and identify what area you want to change. So for example, this hypothetical experiment, we have no communication. So by using the slider, you can shift left or right, depending on whether you want it teacher directed or student directed, and actually build in some communication. So the simplest thing is telling the learner how to communicate. So this could be, for example, writing a lab report or doing a poster presentation or giving an oral presentation. So the learner is actually told how to communicate and justify their conclusions. In terms of the question, so a teacher could provide the question, but if you wanted to make it a bit more student directed, you could actually think about that and actually give the student an option of selecting a question. So when talking to teachers, particularly, they really are hesitant with letting students pose their own question, mainly because they're worried about safety, they're worried about whether they're actually going to get results, they're worried about having the resources for students to actually investigate that question. So often they prefer a learner selecting a question from a list that they know they have the resources for students to actually complete the activity. So from the workshops, we've actually asked delegates to think about what they got out of it. And one thing that was really relevant was, I guess, the educational methods and the experience of doing the experiments that the academics really liked. They also liked talking to other academics at other institutions and being able to do an experiment that someone else is running in their classroom to get ideas, and also get ideas on how they may be able to change their experiments and modify them. Now with the students, I guess they were the one that I really liked was that they didn't realize how much effort staff put into making sure that they have a good learning experience, and that came across quite a lot. So they were surprised by how much effort's being put in. They found it very valuable being able to talk to other academics who are trying very hard to be able to provide them with a very good learning experience. And one workshop in particular that we organized, we even had deans of science being students and completing the experiments alongside all the other students as well. So they had an eye-opening experience. And a lot of the comments that they saw was that they had forgotten what it was like. So that was really important to have that experience. Another thing.
Alex, you have 5 minutes.
Okay. Another thing that was really key was the inquiry slider that they really liked. Oh, that was quick. Okay. So I might just go through the science ed research. I think that's really relevant and something that everyone can take home. So the instruments that we've developed is freely available. One of them is the Student Learning Experience Instrument, which is an instrument that will evaluate a single experiment. So it's designed to test educational issues and to get people to reflect on current educational theories. So there are Likert scale questions as well as open response items. And from the evaluation of that, we can then see whether an experiment is a good experiment or whether it's a poor experiment from the results of that. Now, there are 14 items on this instrument, which are listed here. So they range from data interpretation skills, demonstrators, background, and so on. So what I want you to think about very quickly is which items do you think correlate most strongly with overall lab experience for students? So not what you think, but what do students think correlate strongly with experience? All right, if you want, you can type it in the chat. Which items?
Do you see the chat, Alex, or do you want me to?
Yep. 8 and 11.
8 and 11's coming up quite a lot.
Yep. So demonstrators, teamwork. Yep. 9 and 10. Lab manual. Yep. So that's really interesting. So we surveyed a lot of academics, and this is what the chemistry staff say. So the chemistry academics rated lab skills, interest, demonstrators, and relevance. So lots of those came up today as one that highly correlate. The mid ones were assessment, learning objectives, prac notes, and things like that. And the lowest were data interpretation skills, background, teamwork, and responsibility for own learning. So that hasn't come up at all, I don't think. So then we asked the students. So we asked the students what they thought. So we looked at 54 experiments. We've got over 3,000 responses across multiple year levels. And basically what they think is this. So the ones that correlate highly are understanding, data interpretation, responsibility for own learning, and interest, while the weakest correlations were demonstrators, lab skills, teamwork, background information, and assessment. So demonstrators are teaching assistants. So why are these factors strongly or weakly correlated? So we did a factor analysis, and what we found were 3 groups. So we've got the motivators, assessment, and resources. And basically what we found was that the motivators are the ones that were highly correlated to students' overall experiences. And assessment and resources weren't so highly correlated. So this means that if you were to modify your experiment, you have to firstly collect the baseline, so work out what students actually think first, right? But also the ones that you need or that you can put effort into is the motivators. So if you change and modify and fix one of the motivating factors, then that's going to lead to increased student or positive student experience in the lab. Whereas if you change or modify one of the low like the assessment or resource ones, so for example, background material and demonstrators, yes, they are important, and yes, they do make a difference, but they're not going to make as big a difference as changing or modifying one of the motivating factors. So this means, for example, a demonstrator, look at your teaching assistants. A poor teaching assistant can ruin a really good lab, but a good teaching assistant or demonstrator can't improve a poor lab, if that makes sense. So they're the key things. If you want to put effort, key thing is putting into motivating factors rather than your assessment and resources to start with. because we're all time poor and we need to make sure we put energy into the ones that will make a difference. All right, and I'll just finish on this because I know we've run out of time, but we've also developed the ACL laboratory program evaluation. So this goes hand in hand with the individual experiment one. So the ASLE is one to improve your individual experiments. So trying to get baseline data to see what to improve and get feedback from students. This together with the lab program one, which is distributed at the end of semester, can be used to go hand in hand to improve a course. So for example, an individual experiment might rate poorly, but if you look at the program, it may be put in the wrong spot. So the students may not have covered enough content to be able to do the experiment properly. So if you just move the experiment forward or backwards, it might improve the actual experiment outcomes and overall. Okay, so I won't talk about this because we run out of time, but I'll just quickly get to my final slide. Okay, so my final comments, this is just my perspective, is that we can still have fun as educators developing the learning materials. So by being involved and going into the lab and doing things ourselves will not only help us put ourselves into the shoes of our students, but also be able to improve the experiment for our students as well. Another key thing that I think is really important is using evidence to make change rather than gut feeling. So the instruments that are available uses evidence that students and other academics provide in order to make the improve the experiment. So this not only saves time, but also saves energy. And we have a milestone today where my little girl turned 6 months old. So she's been keeping me very, very busy. But thank you all for listening, and thank you to all the supporting people for the projects that I've been involved in. All right, thank you.
Thank you so much, Alex. That was a wonderful talk. Thank you. Okay, there are a few questions. So one was about the template that you use to design experiment. Is that open source? Is that open access?
Yes.
Where can that be?
So I'll put the website's on the slide. So acl.org.
Yeah.
So on there we have all the school-based experiments, all the university-based experiments, all the templates, the surveys are all on there. And they're open source, freely available. And
two questions came up that were kind of linked together, so I'll try and merge them together. So one was that a comment came in that it was surprising to learn that assessment is not one of the stronger motivators.
Yeah, we were very surprised too.
And also surprising that clear learning expectations is not a good motivator. So can you expand a little bit on those two comments?
So we were really surprised as well. And I guess it comes down, like, assessment is really important, but when it comes to students' experiences, by just knowing what the assessment item is doesn't necessarily mean that they're going to have a good learning experience, if that makes sense. So yeah, so it does correlate, but not as highly. So that's the thing. So it's not that it doesn't correlate, it's just not as high as the other ones that seem to be a motivating factor.
Yeah. Okay, great. Well, thank you so much. In the interest of time, I think we'll move on to our next speaker.